I have previously said that the new science of the 17th century was modeled after rational mechanics and the other mixed mathematical sciences, such as optics and astronomy. The impulse was to exclude from physics any conceptual difficulties, and to exclude the mode of reasoning through conceptual dilemmas, such as what characterizes Aristotelian physics as a sort of speculative philosophizing. Accordingly, rational mechanics and optics provided a template upon which physics might be stripped of all speculative philosophizing and all speculation, and reduced to something of an exact science, which, like those mixed mathematical sciences, would not require the definitions of terms to be subject to dialectical contention, and would not require resolving conceptual difficulties through syllogistic reasoning. Though I hold that to be the motive of the early proponents of the new science, there was also a shift in the way mathematics was performed. Rational mechanics and optics then consisted of geometric proofs, after the manner we find in Euclid. So although those mixed mathematical sciences served as a model for the new physics, although those mixed mathematical sciences served as a model for a new mathematical physics and an epistemological standard for an exact science, they were of a mathematical paradigm very different from the sort of algebraization that emerged not only as a reformulation of mathematics, but as a quantitative physics whereby scientific theories are expressed as algebraic equations. Thus, there must also have been a congruent adjustment within mathematics. There must have been a congruent adjustment within mathematics. Here we arrive at the difference in paradigm between Euclidean mathematics and algebra. I say algebra especially, but I mean modern mathematics generally. Algebra I take merely to be the characteristic manner of modern mathematics. For what we term the quantification of physics, or what we term the reign of quantity, is characterized by a conception of mathematics quite opposed to the previous paradigm of Euclidean mathematics. Nor without algebra could the sort of quantification which we observe to have been, nor without algebra could the sort of quantification which we observe have been totalized, whereby qualities are deemed irrelevant subjective phenomena, and correlations are drawn between variable quantities of different units of measure, as between distances and times, such as that things are considered only insofar as they can be assigned numerical values by measurement and calculation, and certainty is restricted to what can be formulated algebraically. For Euclidean geometry is not so quantitative as to be opposed to qualities, but rather seeks to prove of the different kinds of regular figures what their essential attributes are, their essential properties, or their essential attributes, often being qualitative in nature, and their differences in kind also qualitative. The like is the case with Euclidean arithmetic even, whereby a great deal of importance is placed on qualitative differences between kinds of numbers. For example, two numbers are said to be similar numbers if both are multiples of proportional factors, as are the numbers 6 and 24. Since the factors of which 24 is a multiple, that is 6 and 4, have to each other the same ratio which the factors of which 6 is a multiple, that is 3 and 2, have to one another. That is, as 3 is to 2, so 6 is to 4, 3 and 2 being the sides, so to speak, of 6, and 6 and 4 being the sides of 24. 24 and 6 are thus characterized as similar numbers, much like isosceles triangles are deemed similar figures to one another. The whole of Euclidean mathematics concerns first and foremost the differentiation of kinds of figures as well as numbers, the differences of which are qualitative. Those qualitative differences between kinds of figures and numbers, as well as their essential properties, with which again Euclidean mathematics is primarily concerned, are lost upon the algebraization of mathematics. The homogenization of quantity, whereby everything is reduced through measurement and calculation to what can be expressed algebraically, is as much opposed to the mathematics of Euclid as to the speculative reasoning of Aristotelian physics about conceptual difficulties at the foundations of physics. For whereas modern mathematics and quantitative physics consist in a substratum of algebraic notation and consider things only insofar as they can be assigned numerical values, Euclidean geometry consists of syllogistic proofs, whereby from axiomatic definitions of the kinds or species of mathematical objects, conclusions are inferred regarding their essential attributes. This will become evident upon notice that rational mechanics can only go so far as to geometricize physics. Physics would, albeit, undergo the same process of reduction to the aspects of things relevant to mechanics as weights, lengths, speeds, and times, as indeed the early proponents of the new science declared, that, as they repeated again and again, the only viable explanatory concepts in physics ought only to be the concepts of mechanics, or what can be formulated mechanistically, meaning through the concepts relevant to the science of mechanics, like weights, lengths, speeds, and times. Additionally, conceptual dilemmas, such as whether generation and corruption are different from qualitative alteration, and such conceptual difficulties as are central to Aristotelian physics, would have no place therein, as they did not reappear in modern physics, nor would substantial forms and qualities in general have any place therein. That is, upon a sort of mechanization, upon the mechanization of physics, or the mechanization of the world. But I don't think what is meant by quantification would thereby be reached. The sort of quantification, as René Guénon speaks of in The Reign of Quantity, is but another step, a different step in an alteration of, I say, mathematics. For a physics modeled after rational mechanics and optics and the other mixed mathematical sciences, and aimed at the sort of an exact science which they exemplify, would not result in scientific theories being formulated as algebraic equations. Rational mechanics is not formulated algebraically, nor do mechanical problems call for numerical answers, as neither, for that matter, do Euclidean geometry and arithmetic. Calculation plays hardly any role, if at all, in that sort of mathematics. And we find no equations, nor any manipulating the signs of equations, either for calculation or anything else in the Euclidean paradigm. In which paradigm rational mechanics falls, as also does optics and astronomy, at least before the scientific revolution. The closest thing to a numerical answer in rational mechanics is the drawing of proportions between such quantities as weights and distances. For example, unequal weights attain equilibrium in a balance when the distances the lesser and greater weights are suspended from, when the distances that the lesser and greater weights are suspended from are proportional to their weights, such that the lesser weight is placed at a greater distance and the greater weight at a lesser distance from the fulcrum of a balance, and proportional. Then they attain equilibrium in a balance. But the argument made by Archimedes to establish that proof contains no numerical values whatsoever, and is not reached by manipulating the signs of an equation. Neither even in the arithmetical books of Euclid do we find anything like calculation procedures and equations, let alone in his geometrical books. We find nothing of the sort. That should indicate that a shift must have occurred in mathematics at the advent of algebra and calculus, a shift no less significant than that which occurred in physics, and a shift more foundational that might even be logically antecedent to the shift that occurred in physics. And algebra we find to be the primary characteristic of both modern mathematics and physics. For the quantitative physics of modern science is disposed to draw correlations between heterogeneous quantities, that is, quantities of different units of measure, such as distances and times and weights and speeds, and thus establishes equations of various sorts of different kinds of quantities. But that is the characteristic manner and innovation of algebra. That is what specious algebra, so called, is specifically designed for. And that is what analytic geometry, or the algebra of Descartes, was meant to perform in geometrical problems. That is, between different orders of magnitude, such as between lengths and between areas of surfaces and between volumes of bodies. Whereas that gap is not bridged in that manner in Euclidean geometry or in Euclidean mathematics in general. That is just what differentiates algebra in modern mathematics from Euclidean mathematics. It is, besides the obvious fact that scientific formulae are presented as algebraic equations, they're establishing equations between different kinds of quantities, between quantities of different units of measure, is precisely what distinguishes algebra from Euclidean mathematics. the tension between those two paradigms of mathematics, although revealing of the characteristic manner of quantitative physics, of modern physics, deserves an inquiry in and of itself. And so, although this inquiry resulted from an inquiry into modern physics, we should now turn to the tension between Euclidean and modern mathematics as an inquiry of its own, an inquiry even more important than that between the different paradigms of physics.